Okay, our goal is to understand how buffers can maintain constant pH in blood, for instance, or in any solution for that matter. And we finished off last time saying a buffer is a roughly equal mixture of a weak acid and its conjugate base that can neutralize added challenges of acid or base. Note something that we have one acid here listed as a weak acid, and we have a different acid listed as a challenge acid. And we also have a base that is part of the buffer, and we have a base that could be challenging your buffer situation in the blood. And I want to start off with weak acid. What is a weak acid as opposed to a strong acid? In order to get into that, we're going to go on to the next page and take a look at how we define weak acids. Let's start with acid in general. Here we have a weak acid. It's called acetic acid. It actually is a natural product. It's found in our body, and it is a weak acid. And let's just get into that in a little detail. Any acid can give up a proton, and we can draw that out as a reaction in which the acetic acid gives up its proton and becomes its conjugate base, which we will call acetate. We often use an ATE as a suffix for negatively charged conjugate bases like that. All right, so maybe you remember a little bit about this from general chemistry, that if an acid is very good at giving up its proton, that is, if it mostly dissociates into its base and proton, that is what we call a strong acid. If, on the other hand, the equilibrium lies toward the acid form, and it doesn't give up its proton very easy, that is a weak acid. Now, let's take, for example, this chart down here. Here is acetic acid right here in the middle, and we just said that that is a weak acid. I'm just going to tell you that. It doesn't give up its proton very easily. In fact, most of it stays as the protonated carboxylic acid form if we put it in water. Now that's going to be compared to hydrochloric acid, which is a strong acid, and that tends to give up the whole population would give up its proton and create tremendous acidity. So this is a good start, but we're not really interested in just weak acids and strong acids. We actually want to give a quantitative number to this. And we're going to use the term pKa as a number to describe how strong or weak an acid is. Let me throw some numbers out at you here, and we'll get into them as examples. Acetic acid has a pKa of 4.75. Okay, fine, that's something you can look up in a textbook. What does it mean? Well, we'll come to that in a moment. HCl has a pKa that is less than 0. I forget what it is exactly, -6 or something like that. And that's a strong acid. In fact, we might define strong acids, I think a textbook definition is those that have a pKa of less than -1. Now, what we're really interested in is not just weak or strong acids, as I said, but we're really interested in weak acids and the difference between them. So we're really interested in this area. For instance, you can have the NH4 ammonium ion, which is an acid, and its pKa is 9.25. Now, it is a weak acid as well, but how is it different? It's clearly got a different number there. And the answer is that this, we would say, is a very weak acid. It is not able to give up its proton very easily at all. In fact, if we put the ammonium ion in water, only about 1 in a billion of those molecules would actually give up its proton. So we are really interested in a scale from 0 to 14 for weak acids. And weak acids are all in this range, and the higher the number of the pKa, the weaker the acid is, the less likely it is to give up its proton. really, this pKa idea, which is really the central governing principle around this entire chapter, can be defined in three different ways. The first way is going to be right here. pKa is a measure of how tight a proton is bound. So let's take a look at how this fits into our chart. We said that HCl is able to give up its proton extremely easily, and what we would say for that is that the proton is bound very loose. Comes off very easily. On the other hand, the proton is bound quite tight to acetic acid. That's why when we put acetic acid in water, very little of that acetic acid gives up its proton, and the ammonium ion would be very tight bound to its proton, has a hard time giving it up. This gives rise to this definition, pKa, a measure of how tight a proton is bound. And here's a key take-home for you. Lower in the world of pKa is looser. If you can remember that, lower is looser, it's going to help out a lot, because we're going to look at a lot of molecules, a lot of functional groups. We're going to look at their pKa's, and it's just going to help to know that the lower the pKa is, the easier that proton comes off, because lower is looser. Okay, so pKa is so important for describing weak acids, and we're going to use it a lot. I want to show you that it is a constant. Every acid has an assigned pKa that you can look up in some kind of a reference, and that's always going to be the same. So pKa is a very constant value that describes how tight a proton is bound. We can even look these things up. From time to time, we're going to be interested in particular pKa's of particular acids, and we can look them up in a chart like this one. Here's the ammonium ion. I told you it's 9.25. It shows you the acid form and the base form, ammonia, and it's pKa. Here is acetic acid somewhere along here. Acetic acid and its base, acetate, 4.75. So we can look up pKa values on this chart or in textbooks if we need to. You don't have to memorize them. So this is such an important principle, we're going to practice it a lot. Now we're going to move on, use the concept of weak acid and pKa to really understand the next part of the buffer definition.